Okay, we start. Okay, so chapter 5, as you can see on the screen, I've split into two parts. First part will be on the rigid body motion. We will learn three motion: translation, rotation, and then absolute motion. And later we'll go into chapter 5, number 2, or later on my slide, you'll see chapter 6. We'll do relative motion for the second part. Okay, so the tutorial question that you received today is just the first part. After we complete this tutorial, I'll give you another set. So it's a very long chapter for chapter 5. Okay. So chapter 5 is more on the we already now go into rigid body already. So chapter 1, 2, 3, 4, 1, 2, 3, 4 is on the particle. Means we view the object as one single dot or one big object. But now we start look into the object as a few components like your body. You have head, you have two hands and two legs and body. So we start to see the effect of center of gravity or center of mass. Start from chapter 5 onwards. Okay, now we're going to see what there's a motion, three types of motion. We start to see planar rigid motion. Planar rigid motion means we see the object as is moved on the piece of paper or the plane. So we start to see planar motion. There are three types of motion. First is called translation. If you see on the screen here, on the object, on the rigid body, you mark 2 points or any 2 points, and the object move in a straight line. Means the point move in a straight line. So the top point move to the left, move to the right, bottom point move to the right also in the straight line. So this is called rectilinear translation. In chapter 1, chapter 2, chapter 3, you learn about rectilinear motion. But now, today, we learn about rigid body motion. The first type is called translation, means it's transfer from one location into another location in a straight line. So first one is rectilinear translation. Okay, so translation, the criteria is the two dot must be linked with one line. Within the straight line. So if it's straight line, it become rectilinear. Second one, like what you learn in chapter 1, 2, 3, you have curvilinear motion. So same when we look at rigid body, your point translate in the curve motion and in the linear form. So we have second translation is called curvilinear motion. So you have two type of actually got three translation. You have two types. Rigid body motion, you have three types. So under translation, you have two. One is on the straight line, one on the curved line. If it's moved in the straight line, it's under rectilinear. If it's curvilinear motion, then it's under curvilinear translation. Okay, so these are the two. These are the two type of translation motion: straight line and curve. Second one, first one is translation. Second, planar motion is called rotation. Rotation on the fixed axis, like what you see on the C diagram C. So there is a fixed axis that rotate. It's called rotation on the fixed axis. Usually this one will rotate at the z-axis. If you learn 3D modeling, then this one will be revolve under the function of revolve rotation. So if you imagine a 2D object on the ellipse shape, if you rotate it 180, you get a 3D model like the egg shape. Okay. Okay, rotation, you have axis and also circular path. circular path. You have two key terms here. If you have rotation, you need to find the axis of rotation and also where is the circular path. Okay. So just now, okay. Rotation, translation, rotation. And we have one more. Combination of the previous two. You have translation plus rotation, you get general plane motion. You combine two, you'll get the one at diagram D. It's called general plane motion. It combines translation plus rotation. So each one of the rigid body planar motion have different way of solving it. So you need to be careful and you need to imagine how it reached from, let's say we look at diagram D, how it reached from first position into the final position. It must have a combination from translation plus rotation and then translation again. Okay. So example, so example of application of this rigid body chapter or chapter 5 is when you have all these mechanism in the engine, piston motion, on the motion that require a ring and an arm that can rotate. So these are the example. So as you can see here, on the left, on the piston only can move in one direction. So it's called rectilinear translation. Okay. And on the center here, this ring here is it can only rotate in the one fixed axis. It's called rotational planar motion. And this one also same. Have one pin at the center, far right here, only can rotate at a certain axis. Okay. So and if you look at the combination of two, translation and rotation, is the link here. It's called link. So in the previous chapter 1, 2, 3, 4, you do not see the effect of link, except there's one question in the exercise. If you look into the exercise 12.3 or 12.4 something, all right? So you will see the effect of link. But now in rigid body, you need to consider the link with this connecting the 2 points. So this link is having general plane motion. You need to imagine how the link moving. So this link is moving straight forward. At the same time, because of the this P-ring here, or there's one wheel here. Then this point on the center point here, it will rotate in a circular motion. So it will combine circular plus linear motion. Okay. But again, chapter 5, you need to imagine how the body works, how the body moves. Okay. Two types of fundamental translation, rectilinear, collinear motion, or rotation. It's a combination. When it combines, it becomes general plane motion. Okay. So application in aerospace, this one is very direct. So you should able to give example of all these mechanism, this rotation in all the moving parts in the aircraft and also in satellite. All right. Okay, now we look into translation first. There's an analysis step for translation. So you start to have two axes here. Before chapter 5, you only see one axis. When you go into rigid body, you will start to see more than one axis. So here, we start with, on the left-hand side, the axis X and Y. And we have a start to see reference point O, origin O. Okay, we have one stationary axis, which is, we call it the primary axis. And then you will have one object that stick to the body, we call translating axis. So you have one fixed axis, which is usually in a question, we use the word observer or observing. So that when you observe something, you stick there, you stay there. So our reference point, which is a fixed coordinate system. Then you have one body moving. Then you have you need to put in the translating coordinate system. Okay, so you have two axes. One is for fixed object or fixed reference point, and one for the moving or rotating object. Okay. Once you have the two axes, we always stick to the fixed coordinate system. We always start building the vector or the distant vector from the observing station, which is on the left here, fixed coordinate system O. And then on the rotating or the translating body, the question can fix any point on the body. In this case, the slide here, you have point A and point B. Okay, so you can imagine A is your feet, B is your head. So it can be, if the reference point, your eyes O, look at the A, then you have RA. You have a distance from fixed point O to point A, and you label as vector RA. Same if you look from fixed system O, origin, to point B, then you label as distance R sub B. Once you have this one, and you need to complete the vector diagram. So there is a distance between R and B. R and B. So if you are vector are pointing from A, so from A, the tail and the arrowhead, tail to arrowhead is A to B. How you write the vector form is RB stroke A. So RB stroke A, B stroke A, the stroke means you can replace as a word from or relative to this stroke. B stroke A means if you read this vector is R, the distance from a distance of B or position of B relative to A or from A. Yeah. And when you write the vector equation I teach you before in chapter 1 or chapter 2, you can convert this one RB stroke A equal, convert the stroke become negative. You write RB stroke A equal RB minus RA. Okay. So if you look at the diagram here, the vector diagram, you have a triangular. RB is the resultant. So how you reach O to B, you need to go through RA, continue from A to B. So RB equal to RA plus RB stroke A. Or you get the equation RB stroke A equal to RB minus RA. The same. So this one is under vector mathematics chapter. We will not go deep into there. And I assume you already know how to build vector. Okay, so we start to do. First, we start with the first term. In chapter 1, 2, 3, when you look into particles, we use S as a position. But when we start to look into rigid body, we replace the S, become R. Okay. So all the equation that you learned in chapter 1, 2, 3, S, if you see S, including the Newton equation, if there's an S there, you replace S as R in the equation. Okay. So this one I already explained just now. What is RB stroke A? The stroke, it means respect to or from. The slash B slash A, the slash is mean from or respect to A. There's a direction because it's a vector. It must be from somewhere to somewhere. Okay, so this is the equation. But every time when you solve chapter 5, chapter 6, chapter 7 question, you need to draw the vector diagram or the position diagram. Okay, first you need to identify where is your reference point, where is your observer, where is your stationary point, where do you look from. You need to find the O point. Next, you need to identify what is the moving object that mentioned in the question. On the moving object, there is a point, interest point that mentioned. In this case, on the slide here, you have two interest points, which is A and B. It's on the object. Okay, then you link the position, all position together, you get a triangular. Then you build the triangular. You just need to be sure the RB stroke A this line. Once you have this line, you're able to build the arrow. Okay. So vector addition, you have RB equal to RA plus RB stroke A, or you can write RB stroke A equal to RB minus RA. It's the same. Okay, once we have position that replace S into R, velocity, you know that how to find velocity from position, right? So definition of velocity is what? ds dt in chapter 1 to 3. When it comes to chapter 5, rigid body, you take position, time differentiate it, so you get dr dt. So you still use v to represent velocity, but now you use r as a position for rigid body. So if you write dt, you time differentiate the position, dr dt, drb dt, you get vb, dr dt a, you get va, and rb stroke a, you dt, you get drb stroke a dt. It's a differentiation, huh? Okay, so va, vb, they are absolute velocity. They are absolute velocity with measure from the fixed coordinate system. And we know that velocity of this term, drb stroke a dt, because it's on the body, and these 2 points do not change all the time, like your head and your feet is always the same length. So if you time differentiate the 2 points, you always get 0. There's no change of the position. Because we are here, we are rigid body. Rigid body, you do not stretch it. Okay, so that's why the term drb stroke a dt, you get 0. Now you have bb equal to va, which means VAVB means velocity at point A will same as velocity of point B. Like your head and your feet, if you walk in 2 meters per second, your head will move to the direction 2 meters per second. Your leg also will move in the same speed because they are on the same body. Okay, so this will be the general information for velocity. What about acceleration? Same, huh? Acceleration is you dv dt, you get acceleration, also same, huh? Acceleration also same. So you take dv dt, you get ab equal to aa. So means acceleration also same as the vector of velocity. Okay, so now what is different is you need to start replacing the s term in particle. In rigid body, you use r to represent position, and you start to use relative terms, which is b relative to a, b from a, and so on. Okay. Next, we look into fixed axis. So if an object rotate, you have your axis, vertical axis, as you see on the diagram here, this vertical axis, and you use right-hand rules again. Okay, so if you have an axis and you rotate and we look at the point on the body, we fix as O as the origin, center of the body, and there's one interest point at P, and this P rotate in the circular path. This black dark circle is a circular path. So angular motion, since a point is without dimension, it cannot have angular motion. So only lines or body undergo an angular motion. So angular motion that can only works when you see it as a body. You cannot put a point without dimension to do analysis. So here you have a distance between origin O on the body to the interest point P, we label as R. Yeah. So we're still explaining the diagram. So if your rotation, you have angular position, which is given by the angle. So here on the diagram here, you have one starting reference axis here, or towards this direction. And then your angle is have a direction. So if you use right hand rules, so the direction is anti-clockwise. It's anti-clockwise. As you can see on the diagram, the theta is with the arrowhead here. Okay, positive in this direction. So when there's a change of angle, if you start to rotate, there's a change of angle. So we use d theta or differential angle. We give it a name called angular displacement. Angular means angle. There's a change of angle. So we use the theta as an angular displacement. Okay. So if the change of position, we use R as a rigid body, or in chapter 1, 2, 3, you use S. The rigid body, you use R. And because you have rotation, there's change of angle, we use theta. And change of angle, we use d theta. Okay, so the vector have magnitude measured in degree, radian, and or revolution. One revolution is 360 degree or 2 pi radian. Okay, so these are the common sense. Okay, one revolution is 2 pi radian or 360 degree. Because you need to do conversion later in calculation. And we work with radian most of the time. In chapter 5, 6, 7. We work in radian. Okay, in rigid body, no longer angle unless the question asks you to explain in degree form. Okay, direction is determined by right hand rules, means the curvature of your finger. We're still dealing with vector. Vector have magnitude and also direction. Okay, so we have basically covered all the parameter needed for analysis for chapter 5. So you look at position, determined as R. You look at relative position. You look at angular displacement with theta. And we have looked at 3 types of motion, planar motion. Translation, you have 2 types, linear, circular. Then you have rotation. Okay, combine these two, you get general plane. Yeah. So this is another diagram if you look from the top. Okay, if you look at the top. So you have a circle, right hand rules, anti-clockwise angle, anti-clockwise positive. So we start to introduce angle in velocity, velocity in angle form, which is called angular velocity. We use omega, W in italic form or in a Greek form. We call it omega, angular velocity omega. So when you have angle and you have a time differential of angle, you get omega. Okay, so omega, position positive anticlockwise, and it's like a position also. When you have angle, there's a change of angle, you time differentiate. Omega equal to d theta dt. Okay, so there are two parameters in rigid body. Position, you get r, you time differentiate, you get velocity, and relative velocity, you get acceleration. Another angle from rigid body, you have an angle because of rotation. So rotation you define by angle. So you change the similar principle, angle, there's a change of angle, you dt it. Theta become omega, omega equal to d theta dt. Okay? Or you can see it as velocity in the angle form. Okay, omega, it can be a velocity in the angle form. Mean how fast it turn, how fast it turn. So you start to use radian per second. We start to use radian per second, and not degree per second, it's radian per second. So you need to convert all the angle into radian. In the question, usually give you degree, but you need to convert the degree into radian. Okay. So in the previous section, you see velocity become acceleration, degree become omega or angular velocity. Same, you have velocity, you have acceleration. So if you time differential omega again, you get acceleration, angular acceleration, we define by alpha. Alpha equal to d omega dt. Also anti-clockwise position. That's why from the diagram, a complete diagram for chapter 5, answer usually you will see O, you will see R, you will see interest point ABC, you will see angle in radian or in degree, but you need to convert in radian. You will see a change of angle d theta, and also from the basic information here, either you'll be given omega or you'll be given alpha. So these are the complete diagram or complete parameter that you see in chapter 5. You should able to reverse angular acceleration back to omega or back to velocity by doing integration. Yeah. So how to do integration? For example, alpha equal to d omega dt. You want to find omega. How you do? You move the dt to the left. You do integration. Integration alpha dt, you get omega. Okay, same as the theta also. Same as angular velocity. If you want to get theta, you move omega equal to d theta dt. You move dt to the left. You get integration form. So integration omega dt equal to theta. Change of angle. So same. So it can be the same as what you learned previously in chapter 1, 2, 3. Alpha, it can be also put in terms of the S. Means you double differentiation of your angle. It's the same. So we have defined angular velocity, omega, and angular acceleration, alpha. Or sometimes, if the question gives you when the omega of velocity, angular velocity omega decreasing, then alpha will become angular deceleration because you slow down, you get a negative A or negative acceleration. Deceleration. Mean you slow down. Usually, when this one decreasing, you have a friction. There's something stopping the rotation. Usually, it relates to brakes analysis. Okay. So we have these two. We can start deriving the equation like what we did in chapter 1 and 2 for the Newton equation. So Newton equation, we start putting the dt together. You pull the dt to the left, pull omega down. Pull dt to the left, put alpha down. You combine the two, you will get, yeah, so this is dt equal to d omega. So this one, you pull the dt to the left, you pull omega down, you get this one. And here also same, you pull the dt to the left, you get alpha dt equal to d omega. And you start replacing the dt with d theta, d omega. Okay, you start replacing the center one, dt, with this one. You pull this one here. And you pull, because we need to put the same term together. What you do, you pull the omega to the left, to the right. You arriving at a linear form. Alpha d theta equal to omega d omega. This is just a derivation, but you can memorize later. So this is another new equation for angular motion. Okay. Now, just to simplify, if you remember what you learned in chapter 1 to 3, if you replace alpha as A, d theta, theta is S, omega as V, this is what you see in A ds equal to V dV in chapter 1, when you derive the Newton equation. Okay? Or you can replace all the terms in what you learned in chapter 1. Omega is V, V equal to ds dt, you just replace the theta as S. Same with acceleration, A equal to dv dt, you replace alpha as same as A, acceleration, omega as V. Then you replace the another third equation that you derive, A ds equal to V dV. So replace A as a alpha, S as a theta, omega as V, then you get the angular formula. Okay, again, we are now start into rigid body. Rigid body, you need to use, because of the motion, you have translation and so rotation. That's why we use alpha, omega, and theta term. Okay, now we know that you have these two definitions. Omega equal to d theta dt. Alpha, you have the omega dt. Yeah, I know it's too many information, but we learn. So you can derive the same as what you see in chapter 1. You just replace V equal to VO plus AT. You replace with the omega and alpha. Second equation also same. S minus SO equal VT plus half AT squared. Okay, this will be, you'll be seeing this, the chapter 1, 2, 3 equation in your retest. So make sure you can recall this. The third equation also same. V square equal to VO square plus 2AS, or 2 delta S, or S minus SO. It's the same. So you just need to replace S as a theta, V as a omega, alpha as, A as a alpha. Not yet. Not yet. But this will be the basic formula, and it applies the same also. You can only use this formula when you have constant acceleration, or in this case, angular acceleration. Yeah. Basically, you are just recycling what you learned in chapter 1 to 3, change into rigid body. where you replace the term into rigid body term. And you are recycling all the steps from chapter 1 to 3. Okay. So important, huh? These are the important formula for chapter 5. Okay. So this is the fundamental formula for rotation about the fixed axis. Okay. Now just now is on the body. Yeah. All these things are on the big body where you only involve velocity or omega, acceleration, and angle. Okay. Now, chapter 5 question is a bit weird, a little bit. It will ask you to pinpoint, look into the point there. Right? You do not only look at the body, but it will ask you to focus on that point. Where is that location after 5 seconds or 3 seconds after the rotation? Okay. Okay, there are two types of analysis. First, you need to do body analysis. Second one on point analysis. So point analysis, you start look at the top and then you see a big circle there. And as the body rotate, you know that you are moving, point P moving in a circular motion. So you always have a tangent direction of the velocity. Because you have a circle, so your V always tangent to the circle. And the R is always from the normal direction or R direction from the center to P. Okay. Now we look into the point, not only body, now we look into the point. So position P was defined by the R again. And if the body rotate d theta, you can replace the displacements of P like the circle definition S equal to R theta. You still remember? You still remember when you learn about circle displacement? And you learn about section. This is R, this is S, this is theta. You know that this small section S here, you can define as R multiplied theta. This theta is in radian. This one is in your mathematics. Okay, so you apply the same principle in rigid body point P motion. If you want to find displacement point P to this direction, this P in this direction, so you can know equal to R d theta. This from the circular section mathematic model in radian form. Yeah. So if you look at the diagram, the big diagram on the left, if the P move d theta, also means that if you lock the center and you turn the point, there is a circular displacement ds and the angle. Okay, so you can write ds equal to r d theta. So velocity, we have a definition v equal to ds dt. So what we can do when you focus on point P that move along the circular path, you replace ds equal to r d theta, you will get r d theta dt. Now it's a lot of information on mathematics, but basically you already know already lah. It's just we assembly in the rigid body calculation. V equal to ds dt, or you can write v equal to r d theta dt. Or we know that d theta dt is omega, right? D theta, change of angle, you replace theta as a s, ds, dr is velocity, but rigid body velocity is omega because it's rotate. So you have a omega, angular velocity, omega. So you can write v equal to omega r. So this is also another important 3-mark equation. If you have a rigid body, you can no longer use ds dt anymore. Rigid body, you start to use v equal to omega r. Yeah. Every time you see chapter 5 question, will be the first equation you write on your answer sheet. You write v equal to omega r. Okay, first equation, v equal to omega r. Again, v always tangent to the circular path. So v, if you want to work in the vector form, is actually v equal to omega cross r. But in your test, I won't ask you to do cross products. Okay, dynamic, I don't test you much on the mathematics derivation things, but application of formula. Okay. Okay. So just need to remember, because you're dealing with vector and you're using cross, omega cross r is not same as r cross omega. Direction is different, opposite, directly opposite of each other. So this one is like a screw. You imagine a screw. If you want to tighten, you always tighten clockwise. You want to screw a screw inside a body, you always clockwise. You want to untie the screw, always anti-clockwise. So same as chapter 5. Chapter 5 you see as a screw. So if you want to go out, you always anti-clockwise. You're going to go in the body, you do clockwise. You do clockwise. Okay. So again, I don't test you on the cross products in this module. I just apply. I want you to apply v equal to omega r. That's it. Okay. Okay. Once we have the velocity, we go into acceleration. You see the differences. We change from v into acceleration. V into acceleration diagram. Now acceleration is a bit different when you have circular motion. When you have circular, your acceleration is no longer the ax or ay, because you are moving in circular motion. You are having tangent and normal axis only. So acceleration, you have a normal acceleration pointing towards the center. Yeah. In rigid body, acceleration, normal axis, a normal component always pointing inside the center. Always. When you rotate something, acceleration, normal axis always pointing inside, looking inside the center. And the tangent component will be the same, parallel to the velocity direction, with this tangent direction. So because this is a vector, you have n and t, then you have resultant of A. Okay, resultant of A, how to find resultant? You use trigonometry, an square plus at square square root. Okay, so this one we go very fast. Just recall what you learned in chapter 3 when you have circular motion. At, because it's tangent direction, you use the velocity in tangent direction. dv dt in tangent direction. However, normal, we already memorized this formula. When every time you have circular, an equal to v squared over rho. There is a formula for rho if rho is not given, with a differential equation, which is quite lengthy, but you can find in chapter 3 in circular motion. Okay, so we start to recall back what you learned. So we replace V in terms of omega R, like what we learned previously. V equal to omega R, so we have AT equal to dV dt equal to d omega R dt. And you know that d omega dt equal to alpha R. D omega dt equal to alpha. So AT, you just memorize. If a rigid body, if we ask you to analyze acceleration in tangent direction, you just memorize AT equal to alpha R. V equal to omega R. You just change the V equal to omega. If we ask acceleration, acceleration equal to alpha R. So I want you to see the equation as a left-hand side, right-hand side. Left-hand side is what you learn in chapter 1, 2, 3. The V, acceleration, and all this. On the right-hand side is all the rigid body parameter. Omega, alpha, theta is all on the right. This one is a conversion calculation. It's a conversion between acceleration, that what you learn, acceleration, velocity, and displacement, that what you learn in the chapter 1, 2, 3 in particle form. On the right-hand side is more on the rigid body. Yeah, so it's much easier if you arrange your equation accordingly. So same, you can derive an equal to v square over rho, convert the v as omega r. You square omega r, you get omega square r square. And then you remove the r. So you have omega square r. Because you v equal to omega r, you square it. You get omega square r square. No. You are not doing, you're not doing this one. It's a bit different from a plus b square and ab square. It's a bit, so don't with a plus b square and ab square. Yeah. So here v square equal to omega r with ab square. You get a square b square. So there are two new equations you need to half out or you need to memorize. If the question asks you to find acceleration in tangent, you need to write at equal to alpha r. If the question asks you acceleration in the normal direction or towards the center, an, you need to write an equal to omega square r. You don't need to derive. If you want to derive also can, but you can straight away memorize and then use it. Okay. So this is just what I mentioned just now. If the speed or velocity of p increasing in the tangent direction, then your acceleration in tangent also the same. However, if your speed decreasing, your v drop, your at will act opposite direction of v. It means you get negative a already. You get negative a means you need to slow down the body. You are dealing with vector. If you have positive direction means you are increasing the magnitude. If you slow down means you need to flip the vector direction, arrow back to opposite direction. You need to put in the negative sign. What you need to remember is direction of an. Direction of an in circular body or in rotation rigid body is always pointing inside. There's acceleration pointing inside when you have a circular motion. It's like gravity. You imagine the earth, you are standing on the earth, because the earth always rotate, you're able to stick on the surface. There's acceleration pointing inside, gravitational acceleration pointing inside the core of the Earth. It's the same, huh? Okay, so this one fixed already, huh? Don't create your own direction, huh? Okay, this is the for info, huh? This one for info. You no need to memorize. A equal to dv/dt, and actually it's a cross products because you deal with two terms of vector, and it deal with differentiation. Means you differentiate uv, you will get u dv/dt plus v dv/dt, something like that. You need to use the chain rules. Huh? This one is just for info. Just for info. Huh? Just for info. Just view it. Huh? This is just derivation of all the cross products. I won't test you. It's just for info. Huh? It's involved across products. Detail you can copy from my slide later. Huh? So I want to highlight at the end. At the end, still AT equal to alpha R. AT equal to alpha R. AN equal to omega R. You need to know the direction. Direction of acceleration in tangent always same as your velocity. Or you don't know the velocity, use your right hand rules. The curvature of your finger will be the direction. AN always pointing to the center, O. Don't create your own, huh? It's always pointing inside. Okay. Okay. So now our now is because our R positive direction is always pointing from O outside, but the direction of your normal acceleration is pointing inside. So these are two opposite directions. So what you do, because when we define our R is positive outside, our acceleration will be negative component. When the question give you R always pointing outside, then when you do calculation, remember AN always negative value. Okay. Just now we only define the magnitude AN equal to omega R, but if you given a question R pointing outside positive, then the answer for AN will get negative because it's different direction from the R axis direction. Yeah. There's a difference between the line here, AN equal to omega R. This is magnitude. It's final magnitude, but this is a final answer of your AN. If your axis R is pointing from O towards P, because your vector of AN always pointing inside the center. You put a negative sign there because your vector is opposite direction of the R. Yeah. Okay, the rest is just for info lah. So acceleration, this is a vector analysis. So basically, the resultant of your acceleration is a combination of your AT and AN. So A equal to AT plus AN. And you know that AT is alpha R or this one, alpha R. The cross there is just to let you know it's a cross product. But when you do calculation, you can just take away the cross. You just calculate the AT as alpha R. And then you take alpha R minus the omega square R. just careless mistakes always here on the rigid body. Your AN component is minus. And this one is Pythagoras theorem because you have a vector here. So you can find the resultant as AT squared plus AN squared square root. Okay. And you should be able to find the angle. Angle, it depends, the question asks you to refer to which. You're able to find angle from the trigonometry triangular here. Okay. Okay, so far we are looking at one axis. We have a short break. After the break, we look into relationship of gear. This one. Two body combined together. We stop at here first. Maybe 10 minutes breaks. We continue 12:10. Okay. 10 minutes breaks.